of conjugacy of priors. Okay, so that's why basically posterior is coming as the same form as the prior. Okay, so that's why we could have little bit the life was easier. Okay, we should say. But the problem is that when we are coming into logistic regression, then life is not that easier. So let me share the screen. Can you see my screen? Can everybody see my screen? Okay. So what happens in case of logistic regression? Okay, in case of logistic regression, basically the y is a binary variable. Okay, so it can take the values only 0 or 1. Okay, so the likelihood, the best likelihood I can use, that is Bernoulli. Okay, so here what I'm going to do, that here actually the real problem will be coming, that is Bernoulli and the basically, okay, let me write it down. Yeah, I think it will be easier. So here the p of beta given y comma x, okay, so it will be coming as p of so this is the posterior of beta. I want to find out. So given the data, okay, so that will be coming as y given beta x, okay, multiplied by prior on beta. Okay, so now yi is actually, it is 0 and 1. Okay, that is a binary variable, and xi belongs to, suppose, this p-dimensional vector. Okay, so the likelihood is coming as p of y given yi given beta comma xi. Okay, that is nothing but the sigmoid function. Okay, sigmoid function actually I have already written. So let me write down this sigmoid function. So sigmoid is I'm writing it as sigma. Okay, so that is xi beta. Okay, and this is actually so this is actually coming as, just 1 minute. So what did I write there? Yeah, pi equals to 1 by this one. So, just 1 second. Here log pi and here log of 1 is pi. This is correct. So we are writing it as sigma beta, sigmoid function. Okay, x beta, xi beta to the power yi multiplied by 1 minus sigmoid xi beta to the power 1 minus yi. Okay, so and sigmoid of z is 1 by 1 plus exponential of z minus z. So, okay, so it is almost same. So here it is nothing but, this is nothing but the pi. Okay, in the last slide, and that is nothing but p of y equals to 1 given x. Always. Okay, so it is always like this. So prior on beta, I am taking as, on beta, it is p of beta equals to it is following normal distribution with mean mu 0 and variance, suppose sigma 0 I am taking. Okay, I am taking it multidimensional. Okay, now here problem is there is no conjugacy. Okay, no conjugacy between the normal prior and Bernoulli likelihood. So this is the problem. Okay, so this is the problem why logistic regression needs a different treatment. Means purely Gibbs sampling will not be applicable here. Gibbs sampling is applicable when conjugacy exists in all of the parameters to be estimated. So Gibbs sampling, pure Gibbs sampling is not applicable in logistic regression. Why? So let me iterate it once again that uh, likelihood is by Bernoulli. Okay, likelihood is Bernoulli, but your prior is normal. So here what will happen that here this Z is basically xi beta. Okay, so xi beta. So if you want to take it out, okay, if you want to take it out and work in the fashion what you did earlier, so you will not be able to take it out. Why? Because this is 1 divided by 1 plus exponential of minus x beta. Okay, so taking it out from taking out beta from uh, this particular expression, it's not possible. Okay, it's not possible. So generally what happens that either we use some kind of other kind of sampling inside Gibbs, because Gibbs is for conjugacy only. Okay, it is applicable to conjugacy only. So either you should go by this particular something else inside this Gibbs sampling, or leave that Gibbs sampling aside, okay, and you go for some other kind of methodology, which I'll be discussing tomorrow. Okay, tomorrow we'll be covering this particular variational inference. So in variational inference, basically you'll be seeing that we can actually approximate this kind of logarithmic function. Okay, you can actually approximate this kind of logarithmic function. Okay, using some kind of approximation is there. So we will be using that particular approximation to get a conjugation kind of thing. Okay, so we'll be trying to get a conjugation kind of thing so that we can have normal prior and we can use this um, for finding out the posterior. Okay, so that is how basically we'll be dealing with that, right? So now what is happening, so what we can do that we can find out, we can use normal prior on the beta. Okay, then what will happen that beta this particular normal prior will be used. Now after that what we'll be doing, that we'll be actually using some kind of symmetric random proposal as we had seen in Metropolis Hastings. Okay, so we'll be inputting this particular Metropolis Hastings to sample this particular beta to suit our this non-conjugation. Okay, Metropolis Hastings, okay, they are suited for non-conjugacies, but they are not scaled up in you can say high dimensional scenario. In high dimensional scenario, conjugacy needs to be existing. Okay, so that's why. So let me write it here that Metropolis and Metropolis Hastings both can work under non-conjugacy. Okay, and keep sampling works under conjugacy only. Only. Okay, so here what will happen that what we have to do that we have to actually input this kind of Metropolis or Metropolis Hastings as a can work under non-conjugacy, but not efficient or effective, I should say, effective in high dimensional situation. So we'll be actually implementing this Okay, we'll be implementing this Metropolis Hastings and all these things right now. Okay, after this, then we'll be seeing that Metropolis Hastings, they are not that much effective. Okay, lots of tuning will be required to get a good result. Okay, so but not effective in high dimensional like scenario like give something. It gives. Okay, so that's why what we will be doing, that give something will be using, but will be doing some uh, will be doing some just 1 minute. My slide is having some problem. Okay. So whatever I had written doesn't come. Just 1 minute. Let me check what has happened. So again, so let me write it again once again. So Metropolis and Metropolis Hastings, Metropolis and Metropolis Hastings uh, takes care of non-conjugation, but more in inference. Okay, in high dimensional situation. Okay, give sampling based for conjugate situations, but cannot work under cannot work under non-conjugation. Okay, so this is the problem. So what we are going to do, that will be actually uh, doing give sampling, but inside will be using this particular Metropolis Hastings. Okay, so what we'll be doing, that so let us just take this mm, posterior. Okay, so log of p beta given y comma x. Okay, so it will be log of p uh, of y given beta comma x plus log of p beta. Okay, so this is coming from posterior. Log of posterior is equal to, I'm not using proportionality. Okay, you can use proportionality also, no issues. So log of likelihood plus log of prior. Okay, so log of p of y given beta comma x. Okay, that is actually coming as summation of yi log of sigmoid xi transpose beta, okay, I equals to 1 to n, plus summation of 1 minus yi 1 minus yi log of 1 minus sigma xi transpose beta, equals to 1 to n. Okay, so this is what the likelihood is, log likelihood is. So log likelihood, could you understand, we are actually doing the same thing as we did earlier. Is it okay? Now log of p, uh, this one is the prior on beta is a normal distribution. Okay, so beta is following normal distribution with mean mu 0 and variance covariance matrix as sigma 0. So log of p beta will be equals to, I'm not taking this particular, so full distribution n minus n by 2 or p by 2. Okay, so this is p dimensional. So p dimensional minus p by 2 log of 2 pi minus p by 2 log of sigma naught, okay, plus minus half beta minus mu naught transpose sigma naught inverse beta minus mu naught. Okay, so this is what. So this is a multivariate normal distribution. So I have written it. I think you can relate it from yesterday's multivariate distribution. Okay, now what we are going to do, that we are going to use something called as a proposal distribution. Okay, so in proposal distribution, what I am going to use, that a beta proposal, okay, so beta dash, that will be taken as following normal distribution with beta t minus 1, means in the earlier step what was the beta, based on that basically we are taking proposal value of beta dash with this one as tau square is the variance of that, okay, and I is the identity matrix. Now based on this, what we are going to do, that we are going to compute the uh, acceptance ratio. Acceptance ratio. So what was that called as? Not acceptance ratio, that is called as MH ratio. So acceptance ratio is for the total number of samples. So this is called as MH ratio. So MH ratio we are now taking as minimum of. So we have already done in the last lecture. Okay, so that is minimum of 1 comma p of y given x beta multiplied by beta dash, that is the proposal value, multiplied by p dash divided by p of y given x comma beta t minus 1, that means the earlier step beta value, okay, multiplied by p of beta t minus 1, this one. Okay, this is the ratio, MH ratio, right? So now if we actually take this one, this is acceptable. Yeah, this is yeah. So actually ratio is this one. Ratio is this one, and this is basically the acceptance factor, minimum of 1 comma this one, right? So now this I am taking as R. So R equals to, so log of R basically log of P of y given x comma beta dash plus log of P beta dash minus log of P y given x comma beta t minus 1 minus log of p beta t minus 1. Okay, now if this so acceptance probability is, okay, that is alpha equals to 1 comma mean of 1 comma, so this is mean of 1 comma exponential of log r. Okay, so exponential of log r. So we can, so this is, it's not required here. Yeah. So now how to accept or reject? So generate uniform random number, generate uniform random number, then u, okay, which is belonging to 0 comma 1. If u is less than alpha, then accept. We did this earlier, right? Or reject. So accept the beta naught or else reject the data. Okay, so else reject data this thing and stay with data t minus 1. Okay, so this is what this particular uh, this is called as image within gives. Like this there can be many types of possibilities, okay, you can actually do. So this is the most basic kind of uh, posterior simulation in case of logistic regression. Okay, so this is what it is a mathematics, right? Now I am going to show you the Python implementation. So how many of you are still with me? Earlier Mr. Amar was replying something, now he has also stopped. Are you people there? Yeah, okay, very good. Achha, so now I am going to implement all these things, okay, using Python, and uh, I'll be using this particular uh, simple NumPy and Matplotlib. I'm not going to use any kind of package. Okay, there are some kind of specialized package. There's some kind of specialized package by which you can actually use for uh, which you can use for this computation, patient computation. But I'm not going into that. We'll be implementing using NumPy and Matplotlib only. Okay. So how many of you are having your Python installed? So can you code with me, along with me? Is it possible? Is it possible? Okay, let me just describe the codes. I think that will be more than enough, if you can follow. So first we'll be starting with something called as the estimation of some kind of function value. We'll be using only Python, NumPy, Matplotlib. Okay, I'm not going to use any kind of other kind of packages. There are many specialized packages are there, like PyMC is there, PyStan is there. Then, uh, sorry, can you please come again, Mr. Amar? Mr. Amar, can you please come again? Ins, so I am using VS Code. Okay, that is the ID I am using. You can use any ID. Okay, you can even use Google Colab also, no issues. You can use the Google Colab also, no issues. So first of all, I want to basically show you an spider ID. Okay, that is also good, but IDs are basically this kind of spider ID. Uh, we don't have generally this kind of Jupyter kind of interactive kind of coding. Okay, that few lines you can run. Okay, you can do that, no issues. But the outputs actually you can have the outputs here inside. Okay, so that will be I think much better. That's why I am using Jupyter notebook kind of thing in VS Code. Is it okay? Okay. So first I want to estimate the value of pi. So what is the value of pi? Pi's value is 3.14. Okay, pi's value is 3.14. Is it okay? Pi's value is 3.14. Is it okay or not? Yeah. So now what we are going to do, that this is a very popular kind of example. Okay, this is a very popular kind of example. You can also do some modification in this. I'm just showing you one version of this. Okay, so I'm basically considering a square which is in 0 1 0 1. Okay, so like this 0 1 to 0 1. So what is the area of this? Area will be 1 1 multiplied by 1. Acha, pi's value is approximately 3.14. We are going to do that. We are going to estimate that. Okay, so the square's area, okay, with from 0 1 to 0 1, okay, 0 1 on one side, 0 1 on the other side also. So that area is 1. Is it okay? Yeah, I'll be sending the code. I'll be sharing the codes. Lots of codes are there. I have prepared for today. Like this is a simple, very simple estimation of pi. First of all. Second is I'll be having linear regression using rejection sampling. Then your metropolis testing sampling. Okay, metropolis sampling and then Gibbs sampling. So linear regression as well as logistic regression. So that is basically I want to show you. Okay, and I might ask you assignments on this coding assignment. Okay, just try to understand the code. Try to understand the. Achha, how many of you are having conversant or you are conversant with Python? Little bit coding you are doing. How many of you? Okay, then Mr. Amar, he has told. Anybody else? Or any kind of coding language? May it be Java, may it be any other R programming, MATLAB. So any kind of coding means you should know at least one kind of coding. As now this is Java. So Mr. Arvind, you can actually think of implementing this in Java. Okay, because there's a very lightweight kind of language. Okay, not like Acha. So C also, but you need some kind of packages, okay, because or you might this random number generation, this particular package will be required for Java as well as C, okay, uh, and moreover, it is basically acha, conversion with MATLAB and Python. Okay, so depending upon your skill set, you can actually have MATLAB and Python. They are actually easier to handle in this kind of situations or this kind of problems because there are lots of packages available. Okay, and you need not to do coding from scratch. Okay, whereas if you go for Java, C, and all these things, then you need to code from scratch. Okay, so that is the problem. Suppose if you are doing matrix multiplication also, then also you need to code it from scratch. Okay, in case of Java and C and all these things. Is it okay? So here my aim is to estimate pi. Okay, just installed Anaconda for Python. Which Anaconda you have, or which Python version you have used? You have installed. So I generally use 3.10. I have not gone after that because many of the packages they are having clashes with this 3.11 and 3.12. Many of the packages they're having conflicts. Okay, and Python basically I'll tell 70 to 80% time will go in resolving the conflicts. Okay, 70 to 80% time will be going in resolving the conflicts. That is the main problem. Is it okay? So let me just describe. Just one second. Okay, so here what is happening that I want to estimate the value of pi. Okay, so you can see that if I inscribe a particular 1/4 of a circle inside, or I can take it as -1 to +1. Okay, that is the whole side. Okay, that is the diameter of the circle, right? Then between 0 1 and 0 1 means on the y-axis 0 1 and x-axis 0 1, it will be 1/4 of that circle, full circle, isn't it? 1/4. So from that I am trying to estimate. So what is the method? Python turtle version 3.9. What is turtle, by the way? Turtle is a package, distribution package. You can use anaconda. Win Python was very famous at one time. Acha, turtle is IDE. Okay, no issues. IDE, it is basically based upon your convenience. Okay, it does not have any kind of you can say some kind of specialty. That spider is special. It's not like that. Okay, you can have any kind of ID. You can have even simple notepad and code in that. But the problem is that you have to maintain the indentation. Otherwise, see, if you want to, acha, let me tell you how to install Python. Okay, so if you are not already installed Python, so then I'll tell you. I actually use Miniconda. Okay, I actually use Miniconda. So you can go to this particular Miniconda installer archive. Okay, so let me just write it in the chat box for you people. Whoever has not done this, so go to this one, repo.anaconda.com slash Miniconda, and then find out this. I use Pi 3.10. Okay, 3.10. So you can take this one. I am giving you the full link on it. So this Miniconda I am using. So why I generally don't use Anaconda, full Anaconda distribution? Because what happens that full Anaconda distribution will be having all the packages they are coming. Um, it's almost all the packages. Okay, they are actually coming. Not this TensorFlow, uh, except TensorFlow, PyTorch, and all these kind of specialized packages. Okay, it is having almost all the packages. Now the problem comes that whenever, suppose if you are using a particular package, suppose a graphing package like Plot9 or Plotly, these kind of things. So they need some kind of NumPy version, SciPy version, and all these things. So sometimes it will not allow you to install. Okay, because you are already having some updated packages of NumPy and or updated versions of NumPy and SciPy. So it might not allow you to install that kind of package. This is the problem. So that's why I actually install this Miniconda first, then I create an environment. Okay, or you can actually use this only. So now if you install this, then go to start, then uh, type Anaconda PowerShell prompt. Anaconda PowerShell. Yeah, Google Colab you can use. I'm not telling that I don't have any kind of reservation regarding Google Colab. Okay, you can use it. You can, very nicely. You can actually do many things. Okay, type Anaconda PowerShell prompt. Okay, then this is for local drive. Okay, so I generally don't use Google Colab. Okay, I generally code everything in my local computer only, and I store them. Okay. Achha, so type Anaconda PowerShell prompt, then you'll be getting a link that is Anaconda PowerShell prompt. Go to that. Okay, open that. It will open. It will open one command prompt. Okay, Anaconda command prompt. Okay, and in that you will be installing. Okay, you will be installing the necessary packages. Okay, so you can write this one. Panda install pandas. Achha, so not pandas. It's not required. Spider, Jupiter, then scikit-learn, scikit-learn. So can I use Jupyter Notebook? Yeah, yeah, you can use, no issues. But the problem is that when you are using Jupyter Notebook, that time what will happen that where that notebook is getting saved, you have to find it out. Okay, by default it is going into documents and settings in your users. Beware of that. Okay, Spider, Jupyter, then scikit-learn. then matplotlib. So if you install these four packages, along with this you can use stats models and cborn, stats models and cborn. You can use this. You can install these two packages also. Stats model. Sorry, stats model. No. If you are having Anaconda already, don't remove that. Okay, don't remove that. You are already having everything. You can open a Jupyter notebook or you can open a Spider IDE and you can just start coding that. VS Code is much better in terms of you can say managing all the things. Okay, you can use VS Code, no issues. Okay. Achha. So this is basically and if you install this Spider, Jupyter, Scikit-learn, Matplotlib, stats models, and Seaborn, this will be installing all the dependencies and almost all the packages will be getting. Okay, almost all the packages will be getting. But we'll be using only NumPy and Matplotlib. Okay. To use this NumPy and Matplotlib and another is SciPy package also we'll be using. But if you install this many packages, these 5 to 7 packages, then everything will be coming. Everything. Pandas will be coming, SciPy will be coming, and all other packages also will be coming. Lots of packages actually it is. Is it okay? Should I proceed? Should I proceed? So I was telling about that how to estimate this pi. Okay, how to estimate this pi. So I'm basically considering a 0, 1 to 0, 1 square, and it will be a quarter of circle inside. Okay, that will be having radius as 1. So area of the square is 1. Okay, and area of the quarter circle will be pi by 4. Okay, area of the square will be pi by 4. What my point? Now, what I'm doing, I'm basically generating some points. Okay, I'm generating some points using this sampling mechanism. Now, this is the rejection sampling actually. So, if the point lands outside the circle, then it will be going in the red region. That will be going in the outside circle, but inside the rectangle, inside the square. But if it is the sample is good for us, that means that it is basically landing in the circular portion. Yeah, what kind of error it is giving? Can you tell me? No, stats model and Seaborn that you have to write here only. This so the whole command, the full command will be Conda install Spider, Jupyter, Scikit-learn, Matplotlib, stats models, and Seaborn. Okay. So if you run that command, almost all the packages will be around 500 MB, 500 to 600 MB. It will be downloading. Is it okay? Should I proceed? Please share the code for said method. Which one? This one? Fine. Acha. Okay. So I'm sharing it in. I'm sharing all the codes inside that canvas. You please download. Okay. I'm sharing all the codes inside canvas. Please download. Okay. So here, let me open my canvas. So inside lecture materials I am down uploading. So can you see? No, I have to publish it. So privacy rights. So how to change privacy rights? Choose usage right. I hold the copyright. Material is in the public domain. Public domain. So can you see the codes now in Canvas? Publish. So can you see linear underscore deep sample? Are you able to see? Okay. Okay. So these are some templates you can use. Okay, for doing your own kind of. You play with the codes. I'm telling you. Okay. So can you see all the codes? Just tell me. So pi rejection sampling you can see. Okay, so then let us do the coding. So let me explain it. So now inside the circle basically it will be 5 files, right? No, five or how many? One, two, three, four, five, six, seven. Total seven codes and two files are there. One is my yesterday's session two. Yeah, session two PPT and another was the session one PPT. So can I start? Can I start? Now implementations, I am telling you, implementations are very easy once you have the derivations with you. Okay, so derivations are basically the most difficult part. Can I start? In files, go to files, then lecture material. No, not in inbox. You go to files, then lecture materials. So can you see my screen, coding screen? Should I start?
Yes,
Sorry.
yes, sir. You can start now.
Awesome. So what is happening that you are basically trying to find out that you are generating some samples. Okay, that will be within this square. Now within this square, if it is inside x square plus y square less than equals to, or it is less than the xy if you are generating. So if it is x square plus y square less than equals to 1, then it will be inside the circle. Otherwise, it will be outside the circle if it is more than 1. So this is the logic actually. Okay, so 1 by 1 square you are having, and in that a quarter circle you have drawn, right? And you are trying to sample points which will be uh, thrown into this particular the circular, the quarter circle area. Okay, inside. So here what we are doing, that first we are importing the modules packages. Okay, that is NumPy and Matplotlib PyPlot. Okay, so you have to just you can open these codes in your Jupyter notebook and try to run it. Yeah, yeah, there are total 9 files. One is your, two are your slides. Okay, yesterday's session 1 and session 2, and rest of the files are codes. Okay, so let us start. So now basically what we are doing, that we are generating uh, x coordinate and y coordinate. Okay, how we are generating? We are creating samples from using uniform distribution. Okay, we are creating samples which is following uniform distribution. Okay, now x and y coordinates I have generated, and this x and y coordinate I am putting in the expression x square plus y square, okay, less than equals to 1. If this is satisfied, then the point is inside the circle, and if it is not satisfied, then it is outside the circle. I have to find out that how many of the points they are inside the circle. Is it okay? So what I'm doing, that I'm basically, I have created a function, a very simple function. And one good thing with Python is that it is like English, simple English. Okay, so if you can read it like English, it's not that difficult. So if you are having uh, your logics strong, okay, means if you are having little bit experience in some other language, okay, may it be Java, C++, or anything, okay, it will not be a difficult task for you to understand. And this is very easy actually. That's why we choose Python. Is it okay? So are you running this code? Anybody? Has anybody run this code? Has anybody run this code? Are you getting the output, proper output? Are you getting? Can anybody please respond? Yeah, getting the output, right? Now suppose I am generating only 100 samples. Okay, so if you see that if I am generating 100 samples only, then you can see this is I cannot actually figure out where is the circle area and what is the this thing outside circle. I cannot figure it out that much. Is it okay? So if I suppose, acha, let me just increase the size of these dots. So it is s equals to 1. So here, if I make it s equals to 0.5, so no, s equals to 1 scatter Okay, whatever it has not changed. So here what is happening that this particular blue points, they are inside the circle, and red points, they are outside the circle. Okay, blue points are inside the circle, and red points are outside the circle. So I have generated only 100 points. Okay, so nothing is visible actually. Nothing is properly visible. And what is the estimated pi value? That is coming as 2.88, which is far away from, far lower from this actual pi value. Okay, so if I make it suppose 200, then just check what will happen. You can see now more dense points, little bit dense, and pi is coming as 3.14 10 with 200 samples. Now if I make it suppose 1000, then you'll see that it is coming as 3.02. Okay, now you will be seeing that you can now see that pi is actually it has come down. Okay, earlier it was 3.10, now it is coming as 3.02. It should be more than 3.10 because I am generating 100 samples, right? It should be, but why it is not so? Because all these points are generated randomly. Okay, all these points, they are generated randomly. So your central limit theorem, law of large number, and all these things, they will be basically coming into picture, that they will be telling you sample as much as possible. Okay, you'll be getting more precise result. Okay, sample as much as possible. So instead of 1000, now if I create 5000 samples, then you'll be saying that pi value is 3.16. It is actually more than 3.14. Okay, it's actually more than 3.14. Okay, now instead of in place of 5000, I am taking 10,000 suppose, and 10,000 it is coming as 3.16 again. So a little bit higher than 3.14. Is it okay? Is it okay? Yeah. Also, the circle is coming more and more prominent. Okay, you can actually find it out. Now, if I take suppose 1 lakh samples, okay, so let me see how much it is coming. You can see now that it is exactly 3.136. Okay, which is, yeah, from scipy.stats import 1 minute inverse gamma. Then what are the other things? Inverse gamma. Yeah, scipy you have to install. Yeah, Miss Niti, it is actually it has not installed this scipy. So you do one thing, you go to this Anaconda prompt. Okay, go to this Anaconda prompt and write conda install. Do you have environment installed in there? Can you please speak? If possible, can you please speak up? So
Hello,
do so
sir, I have installed VS Code and that I am using Python
no.
3.11.
Achha, okay. No. VS Code you have Python you have already installed, right? Because
Yes,
VS
yes.
Code is also kind of IDE. It's not
Okay.
having it is not having its own Python. Okay.
Yes,
Okay. So
yes, yes.
if you have already installed Python, then you can actually use this VS Code to work on that. Okay. Okay. So can I proceed? Can I proceed? Okay. So this is just one very simple example of uh, estimating one value. Okay. Of a quantity which is a very well-known quantity, that is pi. Okay, and pi, how we are estimating? We are basically we are drawing a circle, right? And inside that circle we are having a quarters. Sorry, we are having a square, and inside that square we are having a quarter circle. Okay, and that square is unit length square. Okay, that is unit length square, and then we are actually having this particular. We are generating some samples. Okay, randomly. Now these samples are basically coordinates. Okay, coordinates are the points. If the coordinate is suitable for us, then x coordinate to the power 2 plus y coordinate to the power 2, that will be giving you less than equals to 1 value. Okay. Now what you have to find out, that you have to find out pi, and pi is basically here what is happening, that area of the circle is pi by 4. That is the circular area, that is pi by 4. Area is pi by 4 because pi into 1 square, uh, that is the whole circle's area, right? And this quarter circle is having area as pi by 4. So when you are generating the coordinates, and if it is following this x square plus y square less than equals to 1, okay, then it is basically telling you that points in circle divided by total points is approximately pi by 4. So pi will be 4 multiplied by how many points inside the circle and divided by how many points in the total area. Okay, so by that you can actually find out. Is it okay? Now we are going to this particular uh, rejection sample. So can anybody tell me that what is the main you can say logic behind this rejection sampling? Can anybody tell me rejection sampling? What is the logic? It was covered in the very first session, I think. Can anybody tell? Can anybody tell, please? कोई तो बताइए. What is the rejection sampling's main you can say logic? See, rejection sampling, importance sampling, they are the very crude way of doing the samplings. Rejection sampling, yes, rejection sampling. So we are basically generating some sample, right? I have opened, yeah, one predictor, linear regression rejection sampling underscore one pred. That one I have opened. Okay, so let me just run this, and then I'm generating some data. So 50 data points I'm generating, right? With so 50 data points I'm generating. So true beta coefficient, okay, that is the coefficient of the linear regression. So it is one predictor linear regression. So true beta value is 2.5, and the error is having variance standard deviation as 1, so variance is also 1. Okay, and the response value I am generating. Okay, response value I am generating. So let me just plot this. Okay, then I think we'll be seeing that exactly how does it look like. So plot plt dot plot x comma y, plt dot show. So it is coming like this. So let me just change this thing here. It will be suppose O. So it is coming like this. Is it okay? The scatter plot is coming like this. So there is a positive relationship. Okay, the slope is positive. slope is positive. Okay. Now what I'm doing, that we are basically flattening the, for easier, draw samples from the tractable distribution. Yeah, somebody has written, yes, from the tractable distribution q theta, and then only retain those who satisfy the requirement of, yeah, very good. So this is basically I am setting a boundary. I am setting a boundary on the this thing, the parameter to be estimated, right? And I am generating it. I am generating it using the proposal distribution, and then I'm trying to find out that whether it is inside that limit or not, inside that boundary or not. If it is inside that boundary, then I'm using it for calculating the this log likelihood, and I'm basically uh, calculating the posterior. Okay, I'm basically strengthen the posterior. Okay, so in that way will be good. Okay, so here you can see the logic of finding out this. So what is the shape of y? Okay, got it. So now here the posterior is getting calculated. So for that I have created this particular what should I say? Created this particular proposal distribution is uniform distribution. Okay, and if beta is, I have set a boundary that if beta is less than 5 or more than 5, then we'll be rejecting. True beta value is 2.5. Okay, then we are taking log prior as just as 0. Okay, then this particular residuals we are calculating y minus x multiplied by beta. If the beta is inside the minus 5 to 5. Okay, and then log likelihood I am calculating, right? And then returning log likelihood plus log prior, and that is giving me the log posterior. Okay, now this proposal, I have taken proposal distribution is normal distribution, and proposal from the proposal normal distribution I am actually um, sampling this beta. Okay, so then rejection sampling is coming into picture. So samples, that is empty string, empty array. Trials I have taken 0. Okay, I have started with, and then I am generating n underscore samples. Okay, this is a function, that's why it is coming like this. Then beta star, which is the proposal value. Then I am generating a uniform random number, and then target I am creating. Okay, that is log posterior of this particular beta star, exponential of log posterior of this beta star. Then if u is less than the target divided by m into proposal PDF of that beta star. Okay, and we are appending this particular beta star. We'll be appending this beta star if it is following this, if it is satisfying this, and we'll be adding into the trial, right? Then we are finding out what is the acceptance rate. What is the acceptance rate? So acceptance rate is length of the samples divided by trials, and we'll be returning this samples and acceptance rate. Okay, so beta grid I have created, and then ratios I am creating, and m is coming as the max of these ratios multiplied by 1.1. This is just creating a buffer. Okay, this is just creating a buffer, right? Now samples I can generate using this rejection sampling, and you can see that it is working now. I am generating 5,000 samples. Okay, samples generated. Now I am plotting it as a histogram. So I am suppose creating 100 bins. Okay, and then let me run this. Then you will be finding only 2.4% is the acceptance rate, right? And where is the mode? You can find that mode is here. Okay, mode is here, or mean you can say that it will be somewhere here. Okay, so it is near 2.6, but our parameter value, true parameter beta, so true beta is actually 2.5. Okay, so along with this, you can actually create the confidence interval. Exactly that particular value will not be able to generate. Okay, it will be somewhere nearer. And this rejection sampling is not a good kind of sampling. We'll be saying that even Metropolis Hastings, they are also not good kind of samplings. But why we do this? Because sometimes it is a kind of we are having some way out. Okay, that if suppose there is no conjugacy, we are basically we can use this Metropolis Hastings sampling. Okay, many other types of sampling also. Okay, to uh, have a way out. Okay, when you are not having a better. Okay, Acha. So you can actually generate some more samples and you can create. Okay, so suppose if I generate, so I can check that what is the rate acceptance rate. Acceptance is too low. A good sampling mechanism will be having a very high acceptance rate, but you'll be finding this all this rejection, importance sampling, then Metropolis Hastings. Okay, they are not having a good acceptance rate. Give sampling is having very good acceptance rate. Okay, so let me just change the number of samples, increase the number of samples. So here n samples is 1000 I have taken. Instead of 1000 I am giving, sorry, 5000 I have been taken. Instead of 5000 I am taking 10,000. Okay, so 10,000 samples let me generate. Okay, generated. Now you see that acceptance rate is it has a little bit increased. Earlier it was 2 point, how much it was? 2 point, I think it has increased. So now we'll be seeing that the mode is little bit nearer. Earlier it was 2.4. Achha, okay. So let me increase the size little more. Achha, another thing also we can do that we are actually creating this particular acceptance region as -5 and 5. So instead of that, we can take out little, we can squeeze it. Okay, we can squeeze it. So you can actually play with this, right? You can play this code and you can find it out that exactly what is happening. Okay, understood? So now we are going into this linear regression using linear regression for multiple predictors using rejection set. Okay, linear regression using rejection sampling for multiple predictors. So you can see this linear regression rejection sampling underscore multiple pred, multi-pred. Is it okay? So here what we are doing that we are having three parameter, three predictor regression. Okay, and true beta are having value as 2, -1 and 0.5. 2, -1 and 0.5. Okay, so let me run this one by one. Same logic we'll be using. Okay, this particular function log posterior is coming from the earlier one. Okay, so you can copy that and simply paste it here using the same function. Okay, next is proposal mean. I am creating proposal covariance. I am creating. Okay, and then proposal sampler, then proposal PDF. Then going to this rejection sampling, the main loop. Okay, so main function, and then I'm creating 1000 breakpoints, and then generating these breakpoints using uniform distribution. Ratios I am calculating. and then I'm finding out that what is the m value. So m is coming as 0 here, and this is actually having very poor acceptance rate, very poor acceptance rate. So out of 5,000, only point something it is getting accepted. Earlier it was 2.4. So these rejection sampling, importance sampling, as I'm telling you repeatedly, these are uh, very ineffective kind of sampling mechanisms. Okay, very ineffective kind of sampling mechanisms. And if you want to tune it properly, then you have to do many of the improvement in this particular sampling mechanisms. So best is that use in only those cases where there is no way out. Like in logistic regression, as I was telling, that logistic this function, as it is not conjugate to the normal distribution, right? Normal likelihood. So that's why basically normal prior, basically sorry, normal prior and sigmoid function, they are not actually conjugate. Okay, so that's why what you'll be doing, that you'll be using gives you'll be using image inside gives. So this sampling is going on. Are you following my code? Are you running those? Might be in Google Colab, in any other. See, Google Colab, it will be very fast, so you can actually use that. You might not be having that fast computers with you. So it is taking time. Okay, so is it done? Still it is going on. You will be taking some time. Done? No. So by the way, how many of you are research scholars doing PhD or PG student, means a master's student? How many of you are present there? So by it runs, I thought that let me talk to you regarding something. So now it has come, the acceptance rate is 0.29%. Very poor. Very poor. Okay. Acha. Okay. PG. So you are doing PG in NOT, but not done. Acha. Okay. Mine is done. Acha, okay, done. Okay, acha, Richa MCA. Okay. Okay, so let us just plot the marginal histograms. So you can find out uh, the from this plot. Okay, these are the red lines are actually the true value. Okay, true value of the beta, and you can find out the first one is 2, and its mean is around here. Okay, so somewhere in 1.7, 1.8, that side. Okay, and if you take mode, then it is little bit higher than 2. Okay, whereas this particular posterior of beta 1, if you take, then the true value is -1. Okay, and mode is at around -1.335. Okay, around. Okay, this is the one. And the last one is posterior of beta 2. It is almost at the mean, little bit higher side, on the higher side. So it will be around 0.46, and mode is also around 0.4647. Okay, so beta 2 is quite good, but beta naught and beta 1, they are not that good. Okay, you can actually find tell it like this. So you have to do lots of tuning here. Okay, lots of tuning. If you can do, then go ahead. Otherwise, go to next level. Okay, so this is rejection sampling. So I'm not going into importance sampling. I'm now directly going into Gibbs sampling. Okay, I'm going into Gibbs sampling. So Gibbs sampling. So let me start with linear regression with Gibbs sampling. Sarah doing PhD. Okay, PhD in? May I know PhD in? Achha, okay, so let me start with uh, linear regression with Gibbs sampling. Okay, so linear regression is with Gibbs sampling, because normal conjugacy, you can actually have this, as well as inverse gamma conjugacy also. So you can actually use it in a very nice way. Okay, so I'm going to linear regression using Gibbs sampling. Is it okay? Is it okay? So here you need to understand that how to implement this particular Gibbs sampling for linear regression. Okay, and how easy it is actually. So if you are having the expressions ready with you, you can just code in within no time. Okay, but you have to do something while doing the simulation. You have to do some kind of tuning. But this tuning is uh, much lesser than this rejection and importance. Okay, so first is, yeah, you are doing in consumer cognition. That is from marketing area or marketing area, right? Okay, so the next is that I'm generating the data. Okay, I'm generating the data. Okay, no issues, no issues. Later we can discuss. Achha, so generating the data. So true beta value I'm taking 3, 2. Okay, and the true sigma square I am taking value as 1.0. Okay, and based on this I am generating synthetic data. I'm not doing it on real data. Okay, I'm doing it in synthetic data only, and I want to find out that whether my algorithm goes near to this particular true beta values or not. Okay, that is my aim. Is it okay? Is it okay? So now generated the synthetic data. Achha, now some hyperparameters I am taking. Okay, so what are these hyperparameters? Tau 2 means it is the variance of this normal distributed beta. Okay, so one beta I am having prior as normal distribution. and tau 2 is the variance of that particular normal distribution. And a naught and b naught equals to 2 and 1. Okay, so it is actually the they are the values of the gamma distribution. Okay, so sorry, not gamma distribution, inverse gamma distribution. I think it is inverse gamma only. So let me check. Yeah, inverse gamma. Achha, so these are the parameters I have set, hyperparameters I have set. Hyperparameters are the parameters of the parameters. Okay. Achha, now give sampler I am going for 5000 iteration. Beta samples I am creating in this way. This is the empty array. Okay, empty means zero array. Okay, and then initialize. I am initializing with zero value for this beta and sigma 2 as 1, right? And then this is the main loop. Now look at this particular loop, this particular code. Basically, what is happening here? The sigma beta is the inverse of x transpose x divided by sigma 2. So is this getting matched? Is this getting matched? It is basically, okay, let me write down here the markdown. So this is coming as, so this is markdown, right? So markdown. So here, let me write down the expressions of this. Okay, so you can write nicely in the, using latex formula. Okay, you can actually write down the expressions. So that is why I use this notebook. Okay, either it in Jupyter notebook or VS Code. I use, yeah, multiplication symbol is at the rate. Yeah, so for matrix multiplication. So it is sigma beta equals to, okay, this one, math here, x transpose math here, x, okay, and I put it in fraction, so it will be easier. Yeah, matrix case multiplication symbol is, yeah, at the rate. Yes, yes. Or you can do dot product. Okay, so dot is another function. So fraction of this divided by sigma square plus math PF I divided by, or you can take fraction is 1 divided by tau square. So this is the, okay, sigma. Okay, so can you understand this particular equation? Isn't it very nice that I can actually write down the equations here for the code, the corresponding line of code? Isn't it good? So this is actually inverse, right? So to the power minus 1. How many of you know latex? How many of you know latex? See, if you are in research, I'm telling you, go for latex, learning latex. This will help you immensely. Immensely, that will help you. And try to write down your thesis in latex. So next is mu beta. Equals to sigma beta inverse, sigma beta multiplied by sigma beta multiplied by x transpose y multiplied by x transpose y by sigma square. So I am taking this particular x transpose X equal Y divided by sigma square. Divided by sigma square. Okay. So isn't it good? Is it okay? Is it okay? Acha, can you tell me? I actually calculated this particular mu beta. Okay. There I got X transpose sigma beta multiplied by X transpose Y plus something I got, right? What was that? That tau square actually coming, tau square will be coming there. What was that, by the way? That was actually mu beta. That beta is following. So this is actually mu. They are updated. Okay. So these are the updated one. Okay. So these are the updated one, right? So the prior I had taken for beta, it was normal mu beta comma sigma beta square. Okay, that's why we had this X transpose Y divided by sigma square plus mu beta divided by tau square, if you remember. Is it okay? Is it okay? Achha, so now give something how it is getting implemented. That for a number of iterations, what I'll be doing first, I'll be generating beta. Okay, full conditional of beta. Now that is the posterior is normally distributed because my prior is normally distributed. So and it is having conjugacy. That's why. Okay. So mu beta and sigma beta I am calculating first, and then I am generating a sample from that is from multivariate normal distribution. Is it okay? So this is the beta part. So sample beta given sigma 2 comma y. Then I'll be rotating. Okay. So sample sigma 2 given beta comma y. Okay, so for that, what I have to do, that I have to find out that sigma 2 is actually following inverse gamma distribution with alpha and beta. Here it is A0 and B0, right? So A0, how can updated A parameter, how I can find out? AN will be A0 plus number of observations divided by 2. So if you remember, okay. I have let me upload this particular slide also. So I think you open it and you just check it. That would be good for you. You'll be able to follow. So let me share it in Canvas. Canvas. So share it here. So is it okay? Are you understanding or not? You please tell me. Otherwise all my effort will be going in vain. So please check this day 2 session 3 I have sent. I have uploaded in Canvas. Please check. Please check. Is it okay? Now what we are doing, that we are not rejecting any sample. Okay, we are not rejecting any sample. We are whatever sample is getting generated, we are keeping it in our the sequence of samples. Now it will be generating a sequence of samples. So here I am generating here I am generating 5,000 samples. Okay, here I am generating 5,000 samples. Where is the 5,000? Achha, here, okay, this is not a function, this is a loop I have generated. So Now the thing is that I'm plotting it using plotting the histogram of the samples. Okay, so beta naught, the true value is beta naught true value is 3. Sorry, beta naught, I have to find it out. So true value of beta 1 and true value of beta 2 is 3 and 2, right? So beta naught is coming as 3 around. Oh, sorry. No, it is correct, coming correct. So 3 and 2 are the beta values. Okay. So beta 1, it is coming very nicely. That is coming as 3. But beta 2, it is not that good. Okay. So mean is at around 1.85, right? It would have been, means it should have been 2.0, right? Acha. And sigma, we assumed sigma square, we assumed how much it is, we assume that is 2 sigma is 1, and here our sigma is coming as 0.9 around, 0.9 around. Now if I take some more samples, okay, so let me take some more samples. 5,000 samples I have generated, so let us take some more samples. N iter is 5,000. Let me generate suppose 10,000 samples. Okay, and I am using burn-in. So where is that burn-in? Acha, burn-in I have not used here. J, beta samples up to J. What is J? No, burn-in I have not used. So burn-in actually I can use and I can get some more. Now see, uh, okay, it's not that much improved. So burn-in actually I have to check. Okay, so beta samples, one column I am taking. Okay, so instead of this, I'll be taking this for a particular column. I'll be removing first 5,000 samples, suppose. Okay, then I'll be going. Acha, now this kind of sampling mechanisms, they need some kind of diagnostic tests. Okay, so basically we have to check the autocorrelation and trace diagnostics. Okay, so traces should be random like this. Okay, trace plots should be random like this. But if it is a very good sample it is generating, then you will be finding that after this some iterations after this randomness, it will be actually getting stabilized. Okay, actually, if you take this particular the spread of this trace plot, it is actually very less. Okay, it is actually very less. It is from 2.75 to 3.25. That kind of thing. So if you increase that, then you will be getting that it is coming as a line. But uh, the initial value where we are starting, so let us just check this initial value. Okay, so what initial value we have actually started with? What is the initial value I have started with? No, it is not. No initial value it has started with. It is actually generating from the very first iteration itself. Okay, so the confidence intervals you can actually find out 95% confidence intervals on this prediction of a new test point. Okay, so suppose new test point is 1.5 and 1 minus 1.5. Okay, and posterior sample I am generating 1,000 samples I am generating, and I am trying to find out that where it is the what is the prediction of this. Okay, 95% confidence interval on the prediction. So in that way you can actually find. Okay, next is autocorrelation plot. So autocorrelation, the first few iteration. Okay, so here it is showing that in the very first, it is basically autocorrelation. How many of you know autocorrelation? It is basically I have to decide some lags. Okay, so lag 0, it is not used. it is actually of no use actually. So lag 0 means that that will be having highest, the observation with same observation. What is the correlation? Lag 1 is that zeroth observation and first observation, what is the correlation in that way. So in this way, basically, you will be finding for all the lag 1 point, lag 1 these observations, differences, and then you will be finding out what is the autocorrelation. In that way, basically, you will be finding. Now, autocorrelation plot, it is showing that the sampling is very good because that after certain time, this autocorrelation is becoming almost zero. Achha, now posterior credible interval also you can use, you can find out. Achha, what is credible interval? Credible interval is the Bayesian counterpart of the frequentist intervals. Okay, credible intervals are the frequentist counterparts of the Bayesian counterpart of the frequentist intervals. Okay, by that actually you can interpret it. So in this way you can do this, give sampling for a particular regression problem. So let me just do little more. So let me change this p number of variables, suppose 5, and let me do it suppose 3 comma 0 comma minus 3 comma 0 comma 2.0. Okay, so 5 predictors, 5 predictors regression. Okay, now tau is this, n iteration, beta, then sampling is being done. It's done. Okay, and then we are having this posterior, but I have to change this thing. So 10 and this one is 20. Okay, now you can see. Okay, so in this way you can. So it was 3 0, then minus 3 0, and then 2. Okay, so in this way you can find it out. Acha, posterior prediction, let me see. Acha, that will be giving some error because I have taken this x test as a 2-dimensional test points. Okay, because earlier it was 2-dimensional, that's why it is coming like this. Okay, so let me go back to this. Okay, 3 and 0. This one, then this one, then this one, this one, this one, this one. And this histogram should be little bit squeezed. Okay, it should not be too much spreaded. So this is quite good, beta naught. Here it is coming as 3, but here it should be 0, centered around 0, but here it's not centered around 0, it is minus 1.15 around. Okay, so you have to do little tuning of this. Okay, okay, done. Next is I'm going for Metropolis testings, Metropolis for logistic regression. Okay, so logistic regression, what to do in the Metropolis case if I am doing using Metropolis sampling. So how it will be done. So logireg Metropolis. Okay, then generating the data first, and I'm having 5 predictors. Okay, then proposal, then log posterior calculation. So then beta proposal I am calculating and finding out the current and the post proposal. Okay, posterior proposal, and we are accepting based on this random number generation, uniform random number generation. So this acceptance rate is coming as very poor, okay, 0.459, and then it is coming as that posterior mean is 0.35, but true beta was 0.5. Posterior mean is minus 1.275. Anybody speaking? Is anybody asking anything? Yeah, Madam Poonam, yes. Are you asking anything? अच्छा, ठीक है. अच्छा, so in this way we can actually compare the true mean value and true beta value and the posterior beta value. Okay, and we can actually create the trace plot like this. Now trace plots should be kind of stabilized one. Okay, so it is not stabilized. You can see that it is actually moving too much. Okay, so moving too much randomly. Okay, so as I was telling that this metropolis hastings, they are not good for multi-dimensional kind of posterior simulation. They are single dimensional, that is much better. Now, logistic regression for using metropolis hastings. So in metropolis hastings, so we will not be having symmetric proposal. Then, so these are the settings. Then log posterior is calculated like this. So now this is adaptive metropolis parameters I am using. Okay, uh, we can have this kind of non-adaptive also, but I am just did little bit modification in this. Okay, then metropolis sampler I am using. Then Berlin I am discarding. Okay, then I am plotting the trace plots. Okay, you can see that the beta naught is quite good. Beta 1 is not at all good. Beta 2 is also not good. Beta 3 also not good. Beta 4 is very good. Okay, so these beta naught and beta 4, they are quite good because they are centered around the true value. Okay, they are centered around the true value. So now autocorrelation plots, you can find out that autocorrelation, it is diminishing very slowly, very slowly. It should come increasing the lag. It should be very fast. It should decay, but here it is decaying very slowly. So next is credible intervals. You can find out, and then based on the data set and the parameters you have estimated, you can predict for the new observation that what will be the class. Okay, so this is logistic regression using metropolis hastings. Now the last one I'll be doing, that is logistic regression using Gibbs in using image inside Gibbs. Okay, earlier it was only metropolis hastings. Here now we are doing Gibbs within image within Gibbs. Okay, so here two parameter logistic regression I am doing, two predictor. Okay, then you can actually check in this image within Gibbs loop. Metropolis 2 programs, what is that? In Metropolis, yeah, acha, okay. The earlier one, right? No, earlier I did this one, right? Logistic regression with Metropolis hastings. Which one you were talking about? Can you please pick up? So please go through these codes. Okay, and then yeah, Logireg, Metropolis. Yeah, two codes are there. Is it? Are you telling there are two codes? Okay. So that might be just some kind of modification I have done. Logireg underscore Metropolis. No, there is only one code. I don't know. I was doing some kind of experimentation, whatever it may be. So there might be two codes. Okay. So where it is Logireg using Metropolis use with Metropolis. Distance. Yes. So acceptance ratio, there is also very poor, 0.489. Okay, and then I'm plotting the trace plot. Okay, so here also the performance is not good. Actually, for logistic regression, posterior estimation. So I'm closing this. Okay, so let me just discuss. So for logistic regression, generally we actually have little bit more modified versions of modified kind of priors, modifications in priors. One very popular prior is known as polyagama. Okay, so that is known as polyagama. Polyagama. So that polyagama is very nicely actually sampling regarding this, and I tried to show it here, but for Windows version Python, polyagama is not available. Okay, it is not getting installed. I think it is available for this Linux version and Mac version. Okay, so that's why I'm not using it. So this is all for today. So any kind of feedback if you want to give. I know mathematics is really tough, but I'm telling you repeatedly, when we are going to implement it, it will be very easy. Once you have the formula with you, okay, it will be very easy for you to implement. And after that, you have to do some kind of tuning. Is it okay? So should I close it? Should I close it now? So we'll be having more Python sessions tomorrow also. Tomorrow I'll be doing it for the variational inference. First session means after lunch. First session I'll be uh, using variational inference for posterior estimation, and then we'll be going into, and variational inference is much faster. Okay, because it does not go by this kind of sampling mechanism. Okay, so it is much faster. But the problem is it is having some downside also. It actually underestimates the posterior variance. Okay, but the thing is that it is very fast, very fast. Okay, and too much parallelization you can do. So we'll be doing it tomorrow. Okay, so and logistic regression, you'll be finding that there is some method by which uh, even variational inference also, that pure variational inference, it cannot take the non-conjugacy. So we have to make it conjugate. Okay, so we have to make it conjugate. We have to do some kind of approximation so that uh, we can have conjugacies. Okay, so this is what uh, about this particular sampling mechanisms. Right. Tomorrow we'll be starting with Hamiltonian Monte Carlo. That is a little bit tricky. Okay, mathematics is there, and then variational inference. And after lunch, I'll be implementing using Hamiltonian Monte Carlo and this particular variational inference. Okay. So I don't know anything you want to tell, if you want to tell. So if you want to tell anything, how the sessions are going, any kind of feedback, be free. I'm telling you, be free. Okay, this is not a kind of college course where you'll be kind of will not be speaking up. Okay, otherwise your marks will be deducted. Okay, it's not like that. You can give feedback. Okay, very genuine feedback you can give, no issues. Is it okay? Should I close it? Okay. Thank you. Thank you. Yeah, please see the notes. See the notes. Okay.
Thank
See the notes. Okay. Thank you. Shinu, you can close it.